Okay, so this is a part one of a three-part video and it's on energy budget. So the first thing that we need to remember is the electromagnetic spectrum. We went over this in class when we did the flame test. So electromagnetic spectrum is used to describe how entire range of light exists. So when we did the flame test, we used different solutions and we used heat to excite electrons, and when those electrons became excited and they came back, they emitted light. And because of just the way they're made up, the electrons would be excited at in different orbitals, so they will emit different intensity of light, and different intensity of lights have different colors. The other thing that we talked about is that light travel as a wave, right? So the electromagnetic spectrum is arranged by high energy light and low energy light, and then everything in between. The higher the energy level, the shorter the wavelength, meaning the length of a wave, right? Those little wiggly things. So high energy means high frequency, low wavelength, and as it becomes weaker, right, the wavelength becomes bigger and the frequency becomes smaller. So low energy, high energy. Okay. The region that we're going to focus on are infrared, so low energy, visible, that's what we can see, right, and ultraviolet, which from the three of them is the highest energy. The reason we are going to be studying those regions is because here's the sun's energy spectrum, right? So here's the ultraviolet, visible, and ultra-red. So most of the sun spectrum lies, about 43% lies in this region. So that's why we're going to focus on that region. So just a recap: ultraviolet, high energy, short wavelengths; visible, it's in a visible region, so the eye can see; mid energy, mid wavelength; infrared, or sometimes you're going to see as IR. We can think of that as heat; low frequency, low wavelength. Budget is the amount of incoming versus outgoing. So when you think, for example, here's some examples. When you think of money budget, you look at how much you earn versus how much you spend. When we look at the Earth's energy budget, we're going to see how much energy is coming into the Earth versus how much energy is moving out of the Earth. And the whole purpose of this is to reach equilibrium, right? Equilibrium is a state of balance. So here, when we think of equilibrium, we're going to think about how the proportion of incoming and outgoing stays fairly the same, right? Even though the amount per se might change over time. Okay, so this is a model that we're going to refer back over and over again. So here's the sun. The sun emits radiation, and some of that radiation gets intercepted by the Earth, and the Earth goes ahead and absorbs it. So we're going to call this the input of Earth's energy. Yes, the Earth gets some of its energy from deep inside of the Earth, right? We studied that when we studied plate tectonics. We're not going to focus on that right now, so we're going to consider just the primarily input of energy as the sun. And again, the sun emits out infrared, it emits visible, right, and it emits ultraviolet. Once the sunlight reaches the Earth's surface, then what happens? Oh, two things happen. Some of it gets absorbed, some of it gets reflected back. So if we follow this energy, some of it gets absorbed by the atmosphere. Remember, during one of my reviews, I showed you how there's a high concentration of gases in the atmosphere, so those gases will absorb some of that, so it won't reach the Earth. 48% gets absorbed, and then 29% actually gets reflected back. So it gets reflected back to outer space. And this reflection, there's a name, we call it an albedo. That's a measurement. It's measured on a scale from 0 to 1. 1 is high reflectivity, 0 is low reflectivity. So if we look at things that we regularly find, for example, grass, ice, rocks, asphalt, and concrete, which ones do you think have high albedo? Which ones do you think have low albedo? So let's look. So the ocean reflects back about 10 to 60%. Dark roofs usually is about 8 to 18%, so it absorbs a lot of heat. Light roofs usually reflects way better. Okay, and asphalt and concrete absorbs a lot of heat, so this is how much actually is reflected back, 5 to 10%. So if you're someplace that's hot and you're near an asphalt, you're gonna feel a lot of heat. Let's look at forests and crops. Those usually absorb a lot of heat, so they don't reflect a lot back, and that's because they use as for photosynthesis. What I really like to focus on is snow and ice, because those reflect a lot of heat. So they're really important when we're thinking of Earth's albedo, because they reflect a lot of heat back to outer space. So I'm going to show you a video of a scientist actually measuring albedo.
One of the things that I've been studying over the years is albedo, or more generally the distribution of solar radiation in the ice-ocean system. And here at Barra, this provides an interesting case because what we have is called first-year sea ice. And there's more and more of that as the ice cover retreats. And you get some very interesting things, as you can kind of see. One day the ice is flooded with water, and the next day it strains. And I think one of the things that drives my work now is the ice albedo feedback. And that's just a mechanism where when sunlight comes in here in the spring, when this is covered by snow, most of it's reflected. But some of it gets absorbed, and that melts the snow, which starts to melt the surface, and it darkens the surface, lowering the albedo, so you get more sunlight absorbed, and it lowers the albedo even more, and this is what's called a positive feedback. And these positive feedbacks are really of interest for climate purposes, because they're a way that you can take a gentle nudge to the climate system and magnify it into a big shove. And what we're looking at here is to see what's going on in coastal regions, so we can tie it into what's going on in the main ice pack, where we've seen over the past 20 to 30 years a major reduction in the areal extent of sea ice. And one of the things that we believe is that that reduction in sea ice extent is being accelerated by the ice albedo feedback. The spectroradiometer. And on the backpack, there's the electronics for the instrument, which takes light into a fiber optics probe and then splits it up across the spectrum into different colors. This particular instrument is good because it can do the entire solar spectrum from around 350 nanometers all the way out to 2500 nanometers. Now you might wonder why we bother to measure this at all. Well, solar radiation is one of the key parts of the surface heat budget of the Earth. And when you think about it, it's sunlight that keeps the Earth warm ultimately. And so how much of that sunlight comes in is important, and also how much of the sunlight is reflected by the surface is important. And what we're going to do now is go off and measure a quantity called the albedo, which is just simply the fraction of the incident sunlight that's reflected by a surface. First, I have to fire up my computer, while on the back is the electronics that does the optical measurements. The computer is the controller that takes care of the computer, takes care of the instrument, stores the data. Now, before starting the measurements, we've got to boot up the system and do some optimization and calibration of the instrument, which is a process that just takes a couple minutes to do. And on a nice sunny day like today, it's actually kind of pleasant to stand around while the instrument's calibrating itself. But I've been out here in the cold when it's really gotten old waiting on the machine. We have the instrument all ready to go. It's time to measure an albedo. And again, it's going to be a simple instrument. We're going to point this up rotate it and point it down. But there are a few things you really have to be careful of. One is you want the instrument to be level. You don't want to be looking directly at the sun or upside down or anything. And two, you want to pick a site so that it's undisturbed. I mean, who wants to look at the albedos of our footprints? And then finally, you want to make sure that there's no shadows in the field of view. So you're always aiming your albedo measurements toward the sun to avoid the shadowing. And you try to kind of keep the measurement out on your arm as much as possible and keep other people away from the site. So what you do, you just kind of stand here again, looking towards the sun to minimize the shadows. And if you look closely, there's a little bubble level here that helps me level the instrument. Once I get it leveled, I push the button, takes a scan, makes a little song for me so I know it's done it. And I flip it over. Again, get it nice and level. And that's the measurement. And then when we process the data, what we'll do is take those two numbers, determine the ratio, and that's the albedo.
Alright, so the other consideration that we need to take is clouds. So clouds reflect sunlight and need to be included when we think of energy budget. Okay, so this is our model from the beginning, and it's just I have added now the 30% reflected, so we're building an energy budget. So now we have the input and we have some of the output. And then this is a more detailed version. So you have incoming solar radiation. Some of it gets absorbed by the atmosphere, some of it gets reflected by clouds, and then the energy reaches the earth and lots of it gets absorbed, but some of it gets reflected back. And then this process is actually reversed at night, where there's a lot of radiation that leaves the earth but gets blocked by clouds as well as greenhouse gases. Okay, next we're going to move into part 2 in the next video.